The nature of consciousness, science's greatest mystery. Have you ever stopped and asked yourself, what exactly is consciousness? Not in a poetic, philosophical sense, but scientifically. What is it, really, and how does it work? Well, buckle up, because you're about to dive into one of the deepest and most baffling mysteries in all of science, the nature of consciousness. Let's start with the basics. Consciousness is the state of being aware. It's the thing that lets you feel joy, pain, boredom, excitement. It's that inner voice in your head. It's your experience of the world around you and of yourself as an individual within it. But here's the kicker: no one actually knows how it works. Neuroscience has made incredible strides in mapping the human brain. We know what regions light up when we see, hear, touch, and even when we dream. We know how neurons fire, how synapses transfer information, and how certain chemicals affect our thoughts and behaviors. But despite all of this knowledge, no one knows how consciousness emerges from this gray blob of neurons. Let's put that in perspective. Imagine you're building a robot. You give it cameras to see, microphones to hear, a speaker to talk. You load it with software to recognize faces, process language, and respond to questions. Cool, right? But here's what that robot doesn't have: subjective experience. It doesn't feel anything. It doesn't have an inner life. There's no me inside the machine. So the question is, what makes us different? How do electrical signals in the brain give rise to feelings, to awareness, to selfhood? This is what philosopher David Chalmers famously called the hard problem of consciousness. The easy problems are things like how the brain processes input, how we move our bodies, or how memories are stored. But the hard problem asks, why does any of this produce an inner experience? Why doesn't all this brain activity just happen in the dark, with no awareness at all? That's where science hits a wall. There are a few theories out there, of course. Some neuroscientists believe consciousness might emerge from complex computations. Once a system becomes complicated enough, awareness just pops out. Others propose integrated information theory, which suggests that consciousness arises from the way information is shared and connected within a system. Then there's panpsychism, the idea that consciousness might be a fundamental feature of the universe, like space or time, and exists in all matter to some degree. But here's the problem: none of these theories can be tested in a concrete way. We can't even tell for sure whether another person is conscious. We assume it because they act like us. But scientifically, we can't prove it. This is called the other mind's problem. And don't even get started on AI. Can a machine be conscious? If so, how would we know? So why is this mystery still unsolved? Because we're trying to use the brain to understand itself. It's like asking a flashlight to illuminate itself. It might not be possible using our current methods. Add to that the fact that consciousness doesn't show up on a brain scan. We can correlate brain activity with certain experiences, but we can't point to a specific neuron and say, that's where the awareness is. We might eventually crack the code, but for now, consciousness remains the biggest unsolved puzzle in science. So the next time you close your eyes and feel your own thoughts swirling, remember, you are experiencing something so profound and mysterious that even the brightest minds on earth can't explain it. And that is kind of amazing. Dark matter and dark energy, the invisible universe. Take a moment to look around you: your phone, your hands, the air, the stars in the sky. Everything you see and touch makes up what we call ordinary matter. Now, here's the mind blowing part: all of that makes up less than 5% of the universe. That's right. According to modern astrophysics, everything we've ever observed with telescopes, microscopes, or satellites accounts for just a tiny sliver of reality. The rest, it's made up of two mysterious things we can't see, touch, or fully understand: dark matter and dark energy. Let's start with dark matter. Back in the 1930s, astronomer Fritz Zwicky noticed something strange when studying galaxy clusters. The galaxies were moving in ways that didn't make sense, as if something invisible was holding them together. Later, in the 1970s, Vera Rubin confirmed this weird behavior by looking at spiral galaxies. The stars at the edges were orbiting way too fast. According to Newton's laws, they should have flown off into space, but they didn't. It's as if some unseen substance was providing extra gravity, an invisible glue holding galaxies together. That mysterious, gravity producing stuff was dubbed dark matter. Now, fast forward to today. We still don't know what dark matter is. It doesn't emit light. It doesn't absorb light. It doesn't interact with normal matter in any way we can detect, except through gravity. Physicists have tried everything: deep underground detectors, particle accelerators, you name it. But so far, dark matter has evaded every attempt at direct detection. Some theories suggest it might be made up of particles we haven't discovered yet, like WIMPs, weakly interacting massive particles or actions. Others think it might point to entirely new physics beyond the standard model. Bottom line: dark matter is real. We just don't know what it is. And just when you think it can't get any weirder, here comes dark energy. In the late 1990s, two independent teams of scientists were observing distant supernovae to measure how fast the universe was expanding. They expected to find that the expansion was slowing down over time. Instead, they found the opposite. The universe is expanding faster and faster, accelerating. This completely shocked the scientific community. To explain it, scientists proposed the existence of a mysterious force pushing space apart, an anti-gravity energy that fills all of space, but that we can't detect directly. They called it dark energy. And it turns out, dark energy isn't just a little thing. It makes up about 68% of the total energy in the universe. That's the majority of everything. Yet, we have no idea what it is. It might be a property of space itself, a kind of vacuum energy. It might be linked to Einstein's cosmological constant, which he once called his biggest blunder. Or it could be something even more exotic, like a dynamic field that changes over time, sometimes called quintessence. But as of now, it remains a total mystery. So let's break it down. Ordinary matter, everything you've ever known, is just 5% of the universe. Dark matter, an invisible mass holding galaxies together, is about 27%. Dark energy, a force causing the universe to expand faster, is a whopping 68%. That means we don't understand 95% of the universe. Let that sink in. So, why does this baffle science? Because all of our current physics, everything from gravity to quantum mechanics, was built to describe just that 5%. The rest is like a massive cosmic iceberg, hiding just beneath the surface. Until we can unlock the secrets of dark matter and dark energy, we're flying blind through a universe we barely understand. And that's why this mystery continues to haunt the brightest minds in science. The origin of life. Where did it all begin? Have you ever wondered how life actually started? Not how humans evolved from apes or how dinosaurs ruled the earth. Go further back, way back, before cells, before DNA, before anything even remotely alive. The question is, how did lifeless chemicals somehow spark into living, breathing, reproducing life? This question, the origin of life, remains one of the greatest unsolved mysteries in all of science. Let's set the stage. Around 3.8 to 4 billion years ago, Earth was a hot, chaotic place. Volcanoes, lightning storms, asteroid impacts. It was no paradise. And yet, somewhere in all that chaos, life emerged. Single-celled organisms, simple but alive, began to appear in Earth's oceans. From there, evolution took over and gave us everything from jellyfish to giraffes to you watching this video. But how did that first spark of life happen? Science calls this field of study abiogenesis, the process by which non-living matter becomes living matter. And here's where it gets weird. Living organisms are incredibly complex. Even the simplest single-celled bacteria is like a microscopic city with engines, walls, waste systems, and information storage. Inside these cells, DNA carries instructions, proteins do the building, enzymes trigger reactions, and membranes keep everything running in order. So, how do you go from a puddle of random chemicals to this microscopic symphony of life? That's the part we don't understand. One of the earliest attempts to tackle this question was the famous Miller-Urey experiment in 1953. Scientists simulated early Earth conditions by zapping a mix of gases with electricity. The result? They created amino acids, the building blocks of proteins. That was a huge moment. It showed that life's ingredients could form naturally under the right conditions. But here's the thing. Ingredients are not a recipe. Making amino acids isn't the same as making a living cell. Life needs more than molecules. It needs structure, self-replication, metabolism, and, somehow, the ability to evolve. And no experiment has ever successfully made life from scratch. There are theories, of course. Some suggest life started in deep-sea hydrothermal vents, where hot mineral-rich water spews from the ocean floor. Others say it began in shallow pools on land, where chemicals could concentrate and react. Some even propose that life's ingredients came from space, delivered by comets or meteorites. Another idea is the RNA world hypothesis, the theory that RNA, a molecule similar to DNA, might have been the first form of genetic material. It can both store information and catalyze reactions, so it could, in theory, jumpstart life. But even that doesn't explain how RNA formed itself in the first place. We're talking about long, fragile molecules somehow assembling in just the right way to start replicating. It's a bit like shaking a box of Legos and expecting a working spaceship to fall out. And then there's the chicken and egg problem of biology. To make proteins, you need DNA. But to copy DNA, you need proteins. So which came first? Science still has no definitive answer. Why is this mystery so frustrating to scientists? Because life is everywhere, in oceans, deserts, caves, even boiling acid springs. But we only know of one origin point, Earth. If we could find life elsewhere in the universe, or create it artificially in a lab, it might give us the clues we need. Until then, we're left with puzzle pieces, but no clear picture. We know that life somehow emerged from non life billions of years ago, but we don't know the steps. We don't know the timing, and we don't know why it worked. So, where did life come from? Maybe we're close to an answer. Maybe we're still centuries away. Or maybe life is just the universe dreaming of itself. Whatever the case, the origin of life remains one of the greatest scientific mysteries of all time. And that's what makes it so fascinating. The wow signal. Did we miss a message from aliens? On a quiet summer night in 1977, something strange happened. A cosmic whisper that lit up a radio telescope in Ohio and left scientists stunned. It lasted just 72 seconds. No follow up, no repeat, just a mysterious signal from the depths of space. And then silence. It was so bizarre, so unexpected, that when astronomer Jerry Emmons spotted it on a computer printout, he circled it in red pen and scribbled one word in the margin. Wow! And just like that, the signal became legend. It's now known as the wow signal, and to this day, no one knows what it was. Let's rewind a bit. At the time, scientists at Ohio State University were running a project called SETI, the Search for Extraterrestrial Intelligence. They used a massive radio telescope, nicknamed the Big Ear, to scan the skies for unusual radio signals that could possibly come from alien civilizations. On August 15, 1977, the telescope picked up something strange in the constellation Sagittarius, a very strong, narrowband radio signal at 1420 MHz. Now, why is that number important? Because 1420 MHz is the natural frequency of hydrogen, the most abundant element in the universe. SETI researchers have long speculated that if aliens were trying to send a universal hello, this would be a logical frequency to use. And the wow signal wasn't just detectable, it was loud. It peaked at 30 times the background noise. That's stronger than any natural cosmic signal they'd seen. It wasn't like static. It wasn't random. It was sharp, clear, and deliberate sounding. For 72 seconds, it came in strong. And then it vanished. Forever. So, what was it? Well, that's the big mystery. And here's why it still baffles scientists. It didn't match any known astronomical phenomena. Pulsars, quasars, black holes. Nothing we know of naturally produces a signal like that. It wasn't from Earth. The signal didn't match anything from satellites, aircraft, or ground-based transmissions. The telescope's design also ruled out local interference. It never repeated. Astronomers have searched for decades at the same spot in the sky, using better tech, but the signal has never returned. Naturally, people started to wonder. Was it aliens? It sounds ridiculous, sure, but the truth is, no one can rule it out. And when you have no natural explanation, the idea of an intelligent source becomes hard to ignore. Some scientists believe it could have been a brief alien transmission, like a radio lighthouse beam sweeping across the stars. Others think it might have been an accidental leak, like how Earth broadcasts TV and radio into space without meaning to. But even the most optimistic researchers admit we have no proof. It's also possible the wow signal was a one-time natural event we just don't understand yet, something rare and cosmic that mimicked an artificial signal. Others suggest it might have come from something as mundane as a comet, though this theory remains controversial and has never been widely accepted. So, why hasn't science figured this out? Because the wow signal is a data ghost, a single 72-second blip on a 1970s printout. We have no recording of the sound, no repeat signal, no coordinates more specific than somewhere in Sagittarius. In the world of science, you need repeatability to confirm a discovery. And with the wow signal, there's just nothing to test. It's like hearing a whisper in a storm, only once, and then never again. But here's the haunting part. What if it was a message? What if someone or something reached out and we were just too slow to answer? Or worse, what if they're still waiting? Whatever the truth is, the wow signal remains one of the most tantalizing and unexplained moments in the search for life beyond Earth. And until we hear another one, we may never know what or who said hello that night. Ball lightning, the bizarre weather phenomenon science still can't explain. Lightning is wild. We've all seen it. Those sudden bolts that light up the sky, crackling with terrifying power. But what if I told you there's a rarer, weirder, almost ghostly version of lightning that floats, moves sideways, and even enters buildings? It's called ball lightning, and it's one of the strangest and least understood weather phenomena ever recorded. And here's the kicker: science still doesn't know what it is. So, what exactly is ball lightning? Witnesses describe it as a glowing sphere, usually the size of a grapefruit or basketball, hovering in the air during thunderstorms. It can be white, blue, orange, or even green. It moves slowly, sometimes erratically, drifting through the air like it's alive. It can swerve, bounce, or even pass through windows or walls. Some reports say it lasts just a few seconds. Others claim it lingers for minutes before vanishing silently, or exploding with a bang. And yes, people have seen it indoors. Imagine sitting in your living room during a storm, and a glowing orb floats in through the window, hovers in the air for a moment, then fizzles out or explodes with a smell of sulfur. Sounds like something out of a sci-fi movie, right? But here's the thing: ball lightning is real. Thousands of sightings have been reported across centuries, from soldiers in the trenches of World War II, to airline pilots mid-flight, to ordinary people in their homes. Even famous figures have seen it. Nikola Tesla claimed to produce ball lightning in his lab. Russian Tsar Nicholas II supposedly witnessed it float across a church. So, why don't we know more about it? Because ball lightning is unpredictable. It's rare, short lived, and nearly impossible to study under controlled conditions. Most of what we know comes from eyewitness accounts, which, while consistent, are still hard to verify scientifically. Scientists haven't been able to recreate ball lightning reliably in a lab, and without hard data, measurements, recordings, repeatable experiments, it remains a mystery. Over the years, many theories have been proposed. Some say it's a plasma, ionized gas shaped by magnetic fields. Others think it's a chemical reaction triggered by lightning striking the ground, releasing gas that ignites in the air. A few even suggest microwaves trapped in a bubble of ionized air. And yes, the fringe theories are out there too: UFOs, spirits, interdimensional portals. you name it. One 2012 breakthrough came when Chinese scientists accidentally recorded ball lightning with high-speed cameras during a storm. They captured a glowing orb 5 meters wide, lasting about 1.6 seconds. Spectral analysis showed it contained silicon, iron, and calcium, elements found in soil. That gave support to the theory that lightning vaporizes dirt, which then condenses into glowing balls. But even that study raised more questions than answers. So why does ball lightning baffle science? Because it breaks the rules. It doesn't behave like normal lightning. It can float horizontally, appear indoors, move against the wind, and vanish with no trace. Some witnesses say it makes no sound, while others report loud bangs. And there's no consistent explanation for how it forms or why. Plus, it's nearly impossible to predict. You can't just summon a thunderstorm and wait for a glowing orb to appear in your lab. That's not how science or nature works. Yet, it's undeniably real. Thousands of consistent reports across cultures and centuries tell us this isn't hallucination or folklore. Ball lightning is a rare phenomenon that nature still refuses to explain. It's a floating question mark, glowing and drifting through our understanding of physics. And maybe that's why we're so fascinated by it. Because even in our high-tech, hyper-scientific world, there are still mysteries in the sky, lighting up the night with questions we can't yet answer. Déjà vu, a glitch in the matrix, or a glitch in your brain. Have you ever walked into a room, talked to someone, or heard a sentence and suddenly thought, I've been here before, even though you haven't, even though you know you haven't? That strange, creeping feeling that this moment is oddly familiar, like a rerun of something you never actually experienced. That's déjà vu. And to this day, scientists still don't fully understand it. The term déjà vu is French for already seen. And if you've experienced it, you know exactly why it's named that. It feels like your brain is replaying a memory in real time, except there's no memory to replay. For a few seconds, you're absolutely convinced you've already lived this exact moment. Then, poof, it fades, and you're left confused and wondering, what just happened? Now here's the mind-bending part. Déjà vu is incredibly common. Studies estimate that 60% to 80% of people experience it at least once in their lives, especially between the ages of 15 and 25. But despite how widespread it is, science still doesn't have a definitive explanation for it. No one knows exactly why it happens or how it works. It's a mystery that lives at the crossroads of memory, perception, and consciousness. So, what are the theories? Well, researchers have come up with several possibilities, none confirmed, but all fascinating. One leading theory is the dual processing glitch. Your brain processes incoming information in parallel: visual input, sound, spatial awareness. If one of these pathways gets momentarily delayed, the brain might interpret the second version as a memory instead of the original event. Kind of like your brain accidentally saying, hey, I've seen this before, when really, it's just experiencing the same moment twice, milliseconds apart. Another theory focuses on memory errors. Your brain might accidentally misfile a current experience into long-term memory, making it feel like something you've already lived through, even though you haven't. It's like your brain mixes up now with before. Then there's the neurological theory. People with temporal lobe epilepsy often experience déjà vu just before a seizure. This has led some scientists to believe that déjà vu could be a mini seizure like event, a tiny misfire in the temporal lobe where memory and recognition live. But here's the thing, most people who experience déjà vu don't have epilepsy. So while this might explain the mechanism, it doesn't explain why it happens to healthy brains. There are also psychological explanations. Some researchers suggest that déjà vu could be tied to dreams. You might dream of a place, then experience something similar in real life, triggering that eerie familiarity. Others think it could be your brain trying to make sense of a complex or stressful moment, a kind of emotional echo that tricks your memory circuits. And yes, there are more out there ideas too. Some say it's evidence of parallel universes or glitches in the simulation, that eerie moment when timelines overlap or the matrix forgets to refresh. Science doesn't take those theories seriously, but let's be honest. When you feel like you've lived the same moment twice, it's easy to understand why people turn to science fiction for answers. So why hasn't science figured it out yet? Because déjà vu is fleeting, random, and internal. It doesn't show up on scans. You can't predict it. And by the time someone says, wait, I just had déjà vu, the moment is already gone. It's hard to study what you can't observe, measure, or reproduce on demand. And that's why it remains such a slippery mystery. In the end, déjà vu might be nothing more than a glitch in memory, or it could be a window into how our brains stitch time and perception together. Either way, it's a reminder that not everything in the human experience is fully understood. Sometimes your brain taps you on the shoulder and says, hey, we've done this before, even when you haven't. And that's both unsettling and kind of beautiful. Quantum entanglement, the strange science Einstein called spooky. Imagine two particles, tiny, invisible specks so deeply connected that no matter how far apart they are, the state of one instantly affects the state of the other. Even if one is on Earth and the other is across the galaxy, changing one instantly changes the other. No signal, no wires, no delay. Sounds impossible, right? Welcome to the mind-bending world of quantum entanglement, a phenomenon so strange that Albert Einstein himself called it spooky action at a distance. And yes, science still doesn't fully understand it. So what exactly is quantum entanglement? In simple terms, it's when two particles become entangled, meaning their properties, like spin, position, or polarization, become linked. From that point on, measuring one particle's state automatically tells you the state of the other, even if they're separated by millions of miles. It's like flipping a coin in New York, and the second you see its heads, a coin in Tokyo instantly shows tails. Not after a delay. Not after sending a signal. Instantly. Now, you might be thinking, okay, so maybe there's some hidden communication between the particles? That's what Einstein thought too. He didn't believe particles could influence each other faster than the speed of light. That would break the rules of relativity. So he proposed that hidden variables were secretly controlling them behind the scenes. But decades of experiments have crushed that idea. The most famous ones, like Bell's theorem and later real-world tests, showed no hidden signals, no local explanation. Quantum entanglement seems to be real, and it seems to work outside the normal rules of space and time. Here's why it baffles science. Because it challenges our very understanding of how the universe works. In classical physics, the kind that governs cars, rockets, and apples falling from trees, information can't travel faster than light. But with entanglement, it seems like particles are communicating instantly, across any distance. This suggests one of two unsettling possibilities. Information really does travel faster than light, breaking Einstein's rulebook. Space and distance themselves aren't what we think they are. Some scientists believe that when particles are entangled, they're not two separate things at all. They're somehow one single system, even across vast distances. It's like two gloves in two different cities. But instead of thinking of them as two gloves, quantum mechanics treats them as one weird, stretched out object. Reality, at the quantum level, might be deeply interconnected in ways we can't see. Despite how bizarre it sounds, quantum entanglement isn't just theory anymore. Scientists have observed it countless times. In fact, it's the backbone of cutting edge technologies like quantum computing, where qubits can be entangled to perform calculations far beyond classical computers, quantum encryption, promising ultra secure communications, even ideas for quantum teleportation, not moving matter itself, but transmitting quantum information instantly. So while we still don't understand the how or why behind entanglement, we're already starting to use it. But make no mistake, quantum entanglement remains one of the biggest mysteries in all of physics. It hints at a universe that's far stranger, more connected, and more alien than our everyday experiences suggest. We can measure it, we can test it, but we still don't really know what's actually happening behind the curtain. And that's both humbling and thrilling. Because if there's anything quantum entanglement teaches us, it's this: reality is weirder than we could have ever imagined, and we're only just beginning to understand it. The placebo effect: how your mind can heal your body. Imagine taking a sugar pill, something with absolutely no medicine in it, and then feeling your pain melt away, or your depression lift, or your symptoms disappear. That's not science fiction. That's the placebo effect, one of the most mysterious, powerful, and baffling phenomena in all of medicine. And believe it or not, despite decades of research, science still doesn't fully understand how or why it happens. So, what exactly is the placebo effect? In simple terms, it's when a fake treatment, a pill, a shot, even a sham surgery, leads to real improvements in a patient's health. Not because the treatment actually does anything chemically, but because the patient believes it will. Your brain expects healing, and somehow that expectation triggers real changes in your body. Pain decreases, symptoms improve. Sometimes full blown recoveries happen, all because of belief. Now, here's where things get even stranger. The placebo effect doesn't just fool people into thinking they feel better, it can trigger physical changes inside the body. Studies show that placebos can release endorphins, your body's natural painkillers. They can influence heart rate, blood pressure, and even immune system activity. In brain scans, areas linked to pain relief, emotion, and self regulation actually light up during a placebo response, just like they would if a real drug were working. In other words, your brain isn't just pretending. It's actively creating real biological effects based purely on belief and expectation. So, why does this baffle science? because it challenges the traditional view of medicine as something purely mechanical and chemical. We like to think healing happens because we intervene physically, taking a pill, removing a tumor, adjusting chemicals. But the placebo effect suggests that the mind alone can trigger real healing processes. And science doesn't fully understand the pathways that make this possible. Is it brain chemistry? Is it nervous system rewiring? Is it tapping into some subconscious control over the body's repair mechanisms? We don't know. And it raises even bigger, unsettling questions. How much of medical treatment is based on the actual treatment? And how much is based on belief? Could understanding the placebo effect lead to treatments that work without drugs at all? And why do some people respond to placebos while others don't? Another mystery. Placebos work even when you know they're fake. In so-called open-label placebo trials, patients are told, "This is a sugar pill. It has no medicine." And yet, some patients still get better. Think about that. The mind knows the pill is fake, and yet still responds as if it were real. This flips the whole idea of belief on its head and suggests there might be even deeper layers of unconscious healing mechanisms at play. Scientists have tried to dig deeper by studying how placebos work across different conditions. And here's what they found. Placebos are most powerful in conditions tied to subjective experience, like pain, anxiety, depression, and fatigue. They're less effective for purely physical conditions like broken bones or infections, though even then, placebo can sometimes help with symptom management. Factors like trust in the doctor, expectations, and even the color and size of the pill can all influence the strength of the placebo effect. It's a strange, fragile, and still poorly understood phenomenon. In the end, the placebo effect shows us something remarkable. The mind and body are not separate. They're deeply connected in ways we're only beginning to understand. Your thoughts, beliefs, and expectations don't just live inside your head. They reach out and change your biology. And until we fully understand how that happens, the placebo effect will remain one of the greatest mysteries and greatest untapped powers in all of medicine. The Taos hum, the mysterious sound no one can explain. Imagine living in a quiet, peaceful town and constantly hearing a low, rumbling hum. No machines, no obvious source, just a deep, persistent sound like an idling truck engine somewhere off in the distance. You ask your neighbors if they hear it. Some say yes, some say no. You call in scientists to measure it. But sometimes, even with sensitive equipment, they pick up nothing. This is the strange, unsettling reality of the Taos hum, a phenomenon that has baffled residents, scientists, and researchers for decades. And to this day, no one really knows what's causing it. So, what exactly is the Taos hum? It's a low-frequency noise that some people living around the town of Taos, New Mexico report hearing. Descriptions vary, but most say it sounds like a distant diesel engine, a low, persistent rumble, or even a deep, vibrating hum you can feel more than hear. It's not loud, but it's extremely irritating for those who can detect it. Some people say it keeps them up at night. Others report headaches, nausea, and even feelings of anxiety because of the constant, nagging sound. The weirdest part, only a small percentage of the population, around 2 to 5%, seem able to hear it. The rest hear nothing at all. In the early 1990s, the mystery caught national attention. The town of Taos was so disturbed by the phenomenon that they commissioned a formal investigation. Scientists from prestigious institutions, including Los Alamos National Laboratory, the University of New Mexico, and Sandia National Labs, came to Taos to study the hum. They brought sensitive recording equipment, vibration sensors, and electromagnetic detectors. They tested the air, the ground, and even the houses of those affected. And what did they find? Practically nothing. No consistent sound source. No mechanical explanation. Nothing that could account for what so many people were experiencing. It was as if the hum was real, but undetectable. So why does the Taos hum baffle science? Because it seems to sit at the crossroads of perception, physics, and psychology. Here are some of the theories scientists have proposed over the years. Industrial sources. Some thought nearby factories or power plants might be emitting low-frequency noise. But shutting down suspected sources didn't stop the hum. Geological activity. Some speculated that underground seismic movements or vibrations in the Earth's crust might cause the sound. Again, no consistent evidence was found. Electromagnetic fields. Others suggested the hum might be caused by unusual electromagnetic activity, but no measurements have confirmed abnormal fields. Psychological factors. A few researchers even proposed that the hum might be a mass psychogenic phenomenon, a kind of shared auditory hallucination. But that doesn't explain why only a tiny fraction of people can hear it, even when others in the same room hear nothing. Some even wonder if the hum might have an unknown biological cause, like a subtle interaction between human hearing and environmental factors that science simply doesn't understand yet. The Taos hum isn't unique either. Similar hums have been reported in places like Bristol, England, Kokomo, Indiana, and Largs, Scotland. In all these cases, the same frustrating pattern emerges. A small group of people hear a persistent hum. No consistent external source can be found. Scientific investigations come up empty. It's as if the hum exists right at the edge of human perception, real enough to experience, but elusive enough to defy explanation. Today, some residents of Taos have learned to live with the hum. Others have moved away, seeking peace and silence elsewhere. But the mystery remains. Is it a secret of geology, a flaw in human hearing, or something stranger altogether? Until someone finally identifies a concrete source, the Taos hum will stay one of the world's most unsettling, unsolved mysteries. A reminder that even in our high-tech age, there are still things out there, sometimes right under our noses, that we can't yet explain. Why does the universe exist at all? The ultimate mystery. Take a second to look around you. Everything you see, the planets, the stars, the galaxies, the air you breathe, the device you're watching this video on, all of it exists. But here's the mind-bending question. Why? Why does anything exist at all? Why is there something instead of nothing? It might sound like a question for poets or philosophers, but make no mistake, this is one of the biggest scientific mysteries of all time. And despite all our progress in physics, cosmology, and philosophy, we still don't have a clear answer. Let's break it down. Most scientists agree that the universe began around 13.8 billion years ago with the Big Bang. But here's the problem. According to the laws of physics, matter and antimatter should have been created in equal amounts during the Big Bang. And when matter, and antimatter meet, they annihilate each other, leaving behind nothing but pure energy. If the Big Bang had made equal parts matter and antimatter, the universe today should be a cold, empty void with no stars, no planets, no life. And yet, here we are. Somehow, matter won. Somehow, enough matter survived to form everything we see. Why? How? That imbalance, the tiny excess of matter over antimatter, is one of the greatest puzzles in modern physics. Scientists call this mystery baryon asymmetry. They've been searching for ways to explain it. Maybe there were unknown processes in the early universe that slightly favored matter over antimatter. Maybe the laws of physics aren't perfectly symmetrical like we thought. Maybe strange forces or unknown particles tip the scales ever so slightly toward existence. But so far, every experiment, even the most sensitive ones, have come up empty. We still don't know why there's more matter than antimatter. And that's just part of the mystery. Even if we explain baryon asymmetry, the deeper question remains: why is there something instead of nothing? Where did the universe itself come from? Some theories suggest that the universe could have come from a quantum fluctuation, a tiny, random blip in a vacuum that inflated into everything we see. Others propose that our universe is just one bubble in a vast multiverse, where countless other universes are being born and dying all the time. Still others think the laws of physics themselves somehow necessitate existence, that given the right conditions, something had to happen. But all these ideas are still speculative. No one has concrete proof. No one has observed it happening. We are left with a haunting truth. The very existence of the universe is a mystery science can't yet explain. And this leads to even bigger, almost unsettling questions. Could the universe have a purpose? Is there some deeper principle beyond our current understanding of physics? Or are we just the result of a cosmic accident, one random roll of the dice that happened to favor existence over oblivion? Scientists, philosophers, and theologians have debated these questions for centuries, and likely will for centuries more. Because in the end, asking, why does the universe exist, isn't just a scientific question, it's a human one. It touches something deep inside us, the need to understand where we came from, why we're here, and whether there's any meaning behind it all. For now, all we know is this: we exist. The universe exists. And the mystery of why there's something rather than nothing remains one of the greatest, most profound questions science has ever faced. Maybe one day we'll have an answer. Or maybe the mystery itself is part of what makes existence so incredibly, impossibly beautiful. Fast radio bursts, the cosmic signals we can't explain. Imagine you're tuning a giant cosmic radio, scanning the sky, when, out of nowhere, you hear an intense, powerful burst of radio energy. It lasts just a few milliseconds, and then it's gone. No warning, no repeat, just a flash, like a cosmic hiccup, coming from deep space. These are called fast radio bursts, or FRBs. And to this day, they are one of the most baffling mysteries in modern astronomy. So, what exactly are fast radio bursts? First discovered in 2007, FRBs are brief but incredibly powerful pulses of radio waves that seem to originate from far beyond our galaxy. We're talking about a burst of energy that, for a tiny fraction of a second, outshines entire galaxies in the radio spectrum. Yet, they're so fleeting and unpredictable that catching them is like trying to photograph a lightning bolt with a disposable camera. At first, scientists thought the discovery might be a fluke. Maybe it was just interference from Earth-based equipment or some weird glitch. But as radio telescopes grew more sensitive and more powerful, more FRBs started to appear. And here's what made it even weirder. Some FRBs seem to happen only once, a one-time flash, never to be seen again. But others, called repeating FRBs, have been observed to flash multiple times, often at irregular intervals. What's causing these bursts? Why do some repeat and others don't? Why do they seem to come from all over the sky, from places billions of light years away? We don't know. And that's what's driving scientists crazy. Several theories have been proposed. Some researchers think FRBs could be caused by neutron stars, the incredibly dense cores left behind after supernova explosions. More specifically, magnetars, neutron stars with ultra-powerful magnetic fields, might occasionally release giant bursts of energy that we detect as FRBs. Other ideas include collisions between neutron stars and black holes, the collapse of massive stars, or even bizarre phenomena like cosmic strings, hypothetical cracks in the fabric of space-time left over from the Big Bang. Some of the more adventurous theories even propose that FRBs could be signals from extraterrestrial civilizations, using high-powered radio beams to send messages or power spacecraft. Is it likely? Probably not. But given how little we understand about FRBs, nothing is completely off the table. What makes FRBs so baffling is their sheer power and distance. Many FRBs come from billions of light years away. This means the events that created them happened long before humans even existed, and yet their signals are just reaching us now. And the fact that they can release as much energy in a millisecond as our sun does in an entire year is absolutely mind-blowing. How can something so tiny in time and so small in scale produce such an enormous amount of energy? That's still an open question. Scientists are working hard to crack the case. New telescopes like CHIME in Canada and the Australian SCA Pathfinder are detecting dozens of FRBs every year. In 2020, astronomers even detected an FRB from within our own galaxy, associated with a known magnetar. This was a huge clue. It suggested that at least some FRBs could be caused by magnetars. But the full picture is still blurry. Why do some FRBs repeat while others don't? Are there different kinds of FRBs with different causes? What's really going on billions of light years away? No one knows yet. Fast radio bursts remind us that the universe is still full of mysteries. Signals from across the cosmos, flickering on for a millisecond and then disappearing forever, tell us that there's so much we still don't understand. Are FRBs the death cries of dying stars? Are they cosmic accidents? Or are they messages from something or someone far beyond our comprehension? Until we have more answers, FRBs will remain one of the most tantalizing and electrifying mysteries in modern science. The Mpemba effect. Why hot water freezes faster than cold. Here's a simple question. If you put two containers of water in a freezer, one hot and one cold, which one do you think will freeze first? Common sense says the cold water should freeze faster, right? Well, surprisingly, sometimes the hot water freezes first. This strange and counterintuitive phenomenon is called the Mpemba effect, and for decades it has baffled scientists, challenged the laws of physics, and remained one of the weirdest mysteries in everyday life. The story behind the Mpemba effect goes like this. In the 1960s, a Tanzanian high school student named Erasto Mpemba was making ice cream in class. He noticed something odd. When he put hot milk into the freezer, it froze faster than the cold milk. At first, his teachers didn't believe him. After all, it seemed to defy basic logic and physics. But Mpemba was persistent. Eventually, he convinced a visiting physicist, Dr. Dennis Osborne, to run experiments. Sure enough, under certain conditions, hot water did indeed freeze faster than cold water. The phenomenon was named after Mpemba, and a whole new mystery was born. So, what exactly is happening? When we say hot water freezes faster, it's important to understand not always, and not under all conditions, but under specific circumstances, like certain starting temperatures, container shapes, and environmental conditions, hot water can and does freeze more quickly than colder water. And the weird part is, even today, science doesn't fully agree on why. Over the years, scientists have proposed several possible explanations, but none of them fully solve the puzzle. Evaporation. Hot water evaporates faster, meaning there's less water left to freeze. Less water could mean faster freezing. Convection currents. Hot water may set up faster moving convection currents that cool the water more efficiently. Temperature distribution. Hot water might form a temperature gradient where the top cools much faster than the bottom, which could influence freezing patterns. Dissolved gases. Heating water drives out dissolved gases. Water without these gases might behave differently during freezing. Each of these factors seems to play a role some of the time, but no single explanation accounts for all observations. Sometimes evaporation matters. Sometimes convection matters. Sometimes neither seems to fully explain it. It's like trying to solve a puzzle where the pieces keep changing shape. The mystery deepens because reproducing the Mpemba effect isn't always consistent. Some labs observe it under certain conditions. Other labs can't reproduce it at all. Variables like the type of container, the purity of the water, the exact starting temperatures, and even the airflow inside the freezer can all impact whether the effect shows up. It's a complex, messy problem, and nature doesn't always like to give us simple, clean answers. In 2016, a team of physicists from Singapore proposed a fresh theoretical model based on supercooling, where water stays liquid even below its normal freezing point. According to their model, hot water is less likely to supercool compared to cold water, which could make it freeze faster. It's a promising idea, but again, it's not a complete explanation. The truth is, despite all our fancy physics and high-tech experiments, we still don't have a definitive, universally accepted theory for why the Mpemba effect happens. And that's part of what makes it so fascinating. The Mpemba effect reminds us that even in something as everyday and familiar as freezing water, there are still mysteries waiting to be solved. It shows that science isn't just about what we know, it's also about what we don't know. It's a humbling reminder that reality can be stranger than we expect, and that sometimes even a high school student making ice cream can stumble onto a cosmic level mystery. If you enjoyed this look at the Mpemba effect, stick around. There are plenty more bizarre mysteries of science that will leave you questioning everything you thought you knew. The hard problem of dreams. Why we still don't understand why we dream. Close your eyes and fall asleep, and suddenly you're flying through the clouds, meeting people who don't exist, or revisiting places you've never been. Dreams are one of the most fascinating, surreal experiences humans have. But here's the crazy part. Even today, science still doesn't fully understand why we dream. This mystery is called the hard problem of dreams, and it's baffling neuroscientists, psychologists, and philosophers alike. First, let's get clear. We know that we dream. We even know when we dream, mostly during a stage of sleep called REM sleep, or rapid eye movement sleep. Brain scans show our brains are highly active during this phase. It's almost like parts of the brain are awake even while we're unconscious. But the big questions are, why do we dream? What purpose, if any, do dreams actually serve? And that's where the mystery begins. There are lots of theories. Some scientists believe dreaming is just random brain activity. As neurons fire off wildly during sleep, your brain tries to make sense of the noise by weaving it into stories, creating dreams as a kind of accidental side effect. Other researchers think dreams are psychologically important. Sigmund Freud famously argued that dreams reveal hidden desires and fears, things our conscious minds suppress during the day. Carl Jung, another pioneer, believed dreams are a window into the collective unconscious, filled with symbols shared by all humans. More modern theories propose that dreams might help us process emotions, solve problems, or consolidate memories. There's even evidence that people who dream about a task, like a video game or a puzzle, perform better at it the next day. But here's the catch. None of these theories can fully explain why dreams are so vivid, emotional, and often completely bizarre. And none can definitively say why the brain needs to create a full-blown hallucination when it could just quietly process information in the background. This brings us to the real hard problem of dreams. In philosophy and neuroscience, a hard problem refers to something deeper than just figuring out mechanisms. It's about why subjective experience exists at all. When we dream, we don't just experience random flashes of images. We feel emotions. We live through stories. We have entire experiences that feel real at the time. Why doesn't the brain just do its memory cleaning and emotional processing silently? Why does it create a rich, immersive virtual world every single night? This is the hard problem of dreams, and it's tied to the even bigger mystery of consciousness itself, adding even more layers to the mystery. Lucid dreams, where you know you're dreaming and can sometimes control the dream, suggest that some part of self-awareness survives even deep into sleep. Recurring dreams and nightmares hint that the brain might be trying to communicate unresolved issues. Dreams across cultures often share similar themes: falling, flying, being chased, which raises questions about whether there's a deeper, biological purpose behind them. Yet, despite decades of research, there's no universal scientific agreement on why any of this happens. We know bits and pieces. Dreaming seems tied to memory, emotion, and mental health. Dream deprivation leads to cognitive and emotional problems. But the full picture, the real reason our brains craft these nightly movies, is still missing. In the end, the hard problem of dreams reminds us that even as we map the brain down to individual neurons, There are still fundamental mysteries about experience that science can't yet explain. Maybe dreams are vital tools for survival. Maybe they're accidental byproducts of evolution. Or maybe there's something even stranger, glimpses into how consciousness itself works. Until we know for sure, when you close your eyes tonight and step into another dream world, just remember, you're participating in one of the greatest unsolved mysteries of human existence. Tardigrades, nature's ultimate survivors that defy science. Imagine a creature so tough that it can survive the freezing vacuum of space, the crushing pressure of the deep ocean, and temperatures hotter than boiling water. Sounds like science fiction, right? Well, meet the tardigrade, also known as the water bear. These tiny, eight-legged microanimals are some of the most indestructible creatures on Earth. And here's the kicker. Science still doesn't fully understand how they pull it off. Tardigrades are microscopic, less than a millimeter long. You could fit dozens of them on the head of a pin. But despite their size, they're absolute tanks when it comes to survival. Over the years, experiments have shown that tardigrades can survive temperatures as low as minus 272 degrees Celsius, almost absolute zero, and as high as 150 degrees Celsius, way beyond boiling. Intense radiation that would kill humans many times over. Crushing pressures greater than those found in the deepest parts of the ocean. Complete dehydration for decades. Yes, decades. Only to come back to life with a little water. And even the vacuum and radiation of outer space. When humans sent tardigrades on a space mission in 2007, they endured the trip, came back, and kept on living. No other complex organism has shown such resilience. So, what's their secret? Scientists know part of the answer. Tardigrades have a special survival trick called cryptobiosis. When conditions get harsh, they curl up into a tiny ball called a ton, drastically slowing down their metabolism to almost zero. In this ton state, they can survive extreme environments for years, maybe even centuries. It's like pressing a biological pause button. Their bodies produce unique sugar molecules, like trehalose, that help protect their cells from damage. They also make special proteins, like DSUP, short for damage suppressor, which literally shield their DNA from radiation and oxidative damage. These mechanisms are amazing. But here's the weird part. Even with all these discoveries, science still doesn't fully understand how tardigrades survive such extreme extremes. For one, the ton state is incredibly complex. Scientists are still trying to figure out how tardigrades prevent their cells from crystallizing when they lose almost all their water. In most organisms, dehydration shreds cell membranes and proteins beyond repair. But tardigrades somehow preserve their entire biological structure. Also, not all tardigrades survive the same way. Different species seem to use slightly different strategies, suggesting multiple, overlapping methods of survival that we still haven't fully decoded. And while we know about a few key proteins and sugars, how all these systems interact at the molecular and genetic level remains a mystery. How does their DNA repair itself after heavy radiation damage? How do their proteins avoid denaturing in extreme heat? How exactly do they manage near total metabolic shutdown without fatal damage? We're still piecing it together. The mystery of tardigrades matters for more than just curiosity. If we can crack their secrets, it could lead to breakthroughs like better ways to preserve food and medicine, new methods for protecting astronauts from space radiation, potential techniques for organ preservation, extending the time donated organs can survive before transplantation, clues for human survival in extreme environments, even on other planets. In a very real way, tardigrades could hold the key to pushing the boundaries of human exploration and medicine. At the end of the day, tardigrades show us that nature's toolkit is far bigger and stranger than we ever imagined. They're a living reminder that some of Earth's greatest mysteries come in the tiniest, toughest packages. And despite all our technology, all our scientific knowledge, the humble water bear continues to baffle us, surviving where nothing else can, thriving in places we can barely comprehend. Why is yawning contagious? Science still isn't sure. You're watching someone yawn, and before you even realize it, you yawn too. Congratulations. You've just been caught by one of nature's weirdest, most stubborn mysteries, the contagious yawn. It's something we all experience. But here's the wild part. Science still doesn't fully understand why it happens. First, let's break it down. Yawning itself is a pretty strange act. You open your mouth wide, take a deep breath, and sometimes even stretch your muscles. For centuries, people thought yawning was all about getting more oxygen into the body. The theory was that if your blood was low on oxygen, your brain would trigger a yawn to bring in extra air. Sounds simple, right? Well, not so fast. Studies later showed that changing oxygen levels doesn't actually change how much we yawn. Whether you have lots of oxygen, little oxygen, or even breathe pure oxygen, you'll still yawn at about the same rate. So much for that theory. Other scientists suggested that yawning might help cool the brain. Think of it like a natural air conditioner. When your brain gets too hot, a deep breath and a stretch might help regulate its temperature. There's some evidence for this idea. Yawning tends to increase when people are sleepy, bored, or stuck in warm environments, all situations where your brain might need a little cooling. But even if this brain cooling theory holds water, it still doesn't explain the really bizarre part. Why is yawning contagious? Here's where things get even more fascinating. Contagious yawning is so powerful that it can happen when you see someone yawn, when you hear someone yawn, even when you just read or think about yawning. Yeah, you're probably fighting a yawn right now. Not just humans either. Dogs, chimpanzees, and even birds have shown signs of contagious yawning. Why? Some scientists believe contagious yawning could be linked to social bonding. Yawning together might help synchronize group behavior, making sure a pack of animals or a tribe of humans stays alert and cohesive. It could be a primitive form of empathy. Seeing someone else yawn subconsciously triggers a response in you, creating a shared physiological experience. There's even some research showing that people are more likely to catch a yawn from friends, family members, or people they feel emotionally close to, rather than from strangers. This suggests that yawning might be tied to the parts of the brain responsible for empathy and social connection. But, and here's the frustrating part, none of these theories have been definitively proven. Scientists can see the patterns. They know when yawning happens, and they can even track what parts of the brain light up during contagious yawns, like the mirror neuron system, which helps us mimic others' behaviors. But no one can say for sure why the brain responds this way. Is it empathy? Is it group survival instinct? Is it some deep, ancient reflex that we haven't evolved out of? We don't know. And to make things even murkier, not everyone experiences contagious yawning equally. People with certain neurological conditions, like autism or schizophrenia, often experience it differently, suggesting even deeper ties between yawning and the brain's social wiring. In the end, yawning, and especially contagious yawning, remains a puzzle. It's a simple, everyday experience that hints at deep, complex processes inside the human mind. Processes we still don't fully understand. It's a perfect reminder that even the most ordinary moments can hide extraordinary mysteries. So the next time someone yawns near you, and you feel that irresistible pull to yawn too, just remember, you're participating in a phenomenon that science is still trying to figure out. And maybe, just maybe, you're helping to keep the ancient social fabric of humanity alive, one yawn at a time. The bloop, the deep sea mystery that still baffles science. In 1997, scientists listening in on the deep ocean picked up something. Something massive. Something they simply couldn't explain. They called it the bloop, and ever since, it's become one of the greatest unsolved mysteries of the deep sea. Let's rewind for a second. In the 90s, the U.S. National Oceanic and Atmospheric Administration, or NOAA, set up underwater microphones across the Pacific. Originally, they were designed to detect Soviet submarines during the Cold War. But once the Cold War ended, scientists repurposed them for research. That's when, in the summer of 1997, these hydrophones picked up a sound unlike anything ever recorded before. It was ultra low frequency. It was extremely loud, so loud, in fact, that it was detected by sensors over 3,000 miles apart. And most chilling of all, the sound had a strange, organic quality to it, as if something alive had made it. They named it the bloop because, well, it kind of sounded like a deep, echoing bloop. At first, scientists were stumped. The bloop wasn't like the usual sounds of shifting icebergs, volcanic activity, or man made noise. It had characteristics that resembled biological noises, like the calls made by whales or other marine animals, but on a scale far beyond anything known. For a comparison, the loudest known whale sounds, like those from the blue whale, can travel for hundreds of miles underwater. But the bloop was even louder. To create a sound of that magnitude, any creature responsible would have to be far larger than a blue whale, the largest animal ever known to exist. Think about that for a second. An unknown creature, bigger than the biggest animal we've ever discovered, roaming the unexplored depths of the ocean? Yeah, that idea sent shivers down a lot of spines. Naturally, theories exploded. Some thought it could be a giant, undiscovered sea monster lurking in the deep, a new species of supermassive whale, something from the abyss that science had never even imagined. The ocean is still one of the least explored places on Earth. Over 80% of it remains uncharted. So the idea that something huge and mysterious could be hiding down there isn't as crazy as it sounds. Others proposed more rational explanations. Some scientists suggested that the sound might be caused by ice quakes, the fracturing and cracking of giant glaciers as they shift and break apart. These ice quakes can produce extremely loud, low frequency sounds that travel across the ocean. And in 2012, NOAA released a statement suggesting that the bloop was likely the result of ice quakes. Mystery solved, right? Well, not exactly. First of all, even Noah's explanation was cautious. They said the bloop matched icequake sounds in many respects, but didn't confirm it with absolute certainty. And skeptics pointed out that the organic quality of the sound, the way it rises and falls, almost like a biological call, was hard to fully reconcile with simple shifting ice. Plus, other strange deep sea sounds have been recorded over the years, like Julia, upsweep, and slow down, each with their own eerie mysteries, suggesting that we still don't fully understand what's happening in the deepest parts of the ocean. The bloop remains a symbol of our ignorance of the deep sea. Even today, the majority of ocean life remains undiscovered, and strange noises continue to drift up from the abyss, begging for explanations. So, was the bloop just a natural phenomenon? Or was it something else? Something alive? Something enormous? Something we haven't yet seen? We still don't know. And maybe that's the most exciting part. In a world where we think we've mapped everything, where satellites photograph every inch of land, the ocean reminds us that some mysteries are still truly, wonderfully unsolved. The bloop continues to echo across scientific debates and into our imaginations, because sometimes the unknown is far more powerful and far more fascinating than any answer we could ever hope for. The mystery of animal migration. How do they know where to go? Every year, across oceans, continents, and entire hemispheres, millions of animals make impossible journeys. Monarch butterflies flutter thousands of miles to Mexico. Arctic terns migrate from the North Pole to the South Pole and back again. Sea turtles, after decades wandering the oceans, somehow return to the exact beach where they were born. It's called animal migration, and it's one of the most astonishing, and still deeply mysterious, phenomena in nature. How do they know where to go? How do they navigate across thousands of miles, often without ever having made the journey before? The truth is, science still doesn't fully understand it. First, let's understand what migration really is. Migration isn't just moving around randomly. It's a precise, predictable, and often unbelievably accurate movement from one location to another, usually triggered by changes in seasons, food availability, or breeding needs. What makes migration so baffling is that many animals perform these journeys without any maps, compasses, GPS, or Google Maps. And some creatures, like newborn sea turtles and juvenile birds, manage to migrate successfully without even being taught by older members of their species. It's like they're born with the destination already programmed into them. But how? Scientists have uncovered a few fascinating clues. Some animals seem to use the sun and the stars for navigation. For example, indigo buntings, a type of bird, have been shown to navigate using the night sky, specifically recognizing constellations. Other species appear to detect the Earth's magnetic field, a phenomenon called magnetoreception. There's evidence that animals like sea turtles, pigeons, and certain types of fish have internal compasses that allow them to feel the Earth's magnetic forces and use them like a GPS signal. Some creatures even combine multiple methods: the sun by day, the stars by night, magnetic fields when skies are cloudy. But, and here's the kicker, even though scientists have identified these tools, they still don't fully understand how animals use them so precisely. For example, where exactly is the magnetic sensor in a turtle's brain or body? How do birds correct for winds, storms, and changing environmental cues without getting lost? The mechanisms remain stubbornly elusive. Even more mysterious is how instinct plays a role. Take monarch butterflies. Each migration from Canada to Mexico spans about 3,000 miles, but a single butterfly doesn't make the entire journey. Instead, it takes multiple generations, up to 4 or 5 different butterfly lifespans, to complete the round trip. Think about that. The butterflies that arrive in Mexico have never been there before. Their great grandparents made the first trip, and yet, somehow, they know exactly where to go. This suggests a kind of genetic memory, a hardwired instinct passed down through generations. But again, how this memory is stored and activated in such tiny creatures remains an open question. There are even stranger mysteries. Wildebeest in Africa migrate in huge, synchronized herds, but how do they all know when to move? Salmon return to the exact river they were born in. How do they smell or sense their birthplace after years in the open ocean? Whales sing complex songs during migration. Could sound be part of a hidden navigation system? Each answer scientists uncover only seems to raise more questions. Animal migration is a dance between instinct, environment, and an inner compass that we still don't fully understand. In the end, animal migration remains one of the great marvels of the natural world. It reminds us that nature still holds secrets, deep, intricate secrets encoded not just in landscapes, but within the animals themselves. Secrets that no satellite, no supercomputer, and no laboratory has fully unraveled. Maybe someday we'll finally decode the full story behind these epic journeys. But for now, we can only marvel at the mystery and follow from afar the incredible travelers who cross the world without ever asking for directions. Near death experiences, science's unsolved mystery. What happens when we die? It's a question that's haunted humanity for thousands of years. And sometimes, people who come close to death, or even momentarily cross the line, come back with incredible stories. Stories of tunnels of light, of floating above their own bodies, of meeting loved ones who had already passed away. These are called near death experiences, or NDEs. And despite decades of scientific research, no one fully understands them. First, what exactly is a near death experience? It's typically described as a profound psychological event that occurs when a person is either clinically dead or very close to dying. Common features include a feeling of peace and detachment from the body, moving through a tunnel toward a bright light, experiencing a life review, reliving key moments from one's life, meeting deceased relatives or spiritual beings, feeling a choice or a need to return to the body. These experiences can happen to people who survive cardiac arrest, trauma, severe illnesses, or even during surgical operations where brain activity has flatlined. And what's most baffling is that NDEs are remarkably consistent across cultures, religions, ages, and even time periods. Whether you're a farmer in ancient China, a nurse in modern day New York, or a teenager in ancient Greece, the basic elements of NDE show up again and again. Now, why does this baffle science? Because, under current medical understanding, conscious experience requires a functioning brain. Neurons must be firing. Electrical activity must be active. But many people report vivid, structured experiences at times when their brain was supposedly inactive or severely impaired. In some cases, patients are clinically brain dead, or their brain activity is so low it should be impossible to form coherent thoughts, let alone have complex, emotional experiences. And yet, they describe incredibly detailed scenes, sometimes even recounting events that happened in the room while they were unconscious. How is that possible? Scientists have put forward a few theories. Some suggest that NDs are the brain's response to extreme stress. When the body is near death, it floods itself with chemicals like endorphins and serotonin, which could create hallucinations and feelings of peace. Others propose that lack of oxygen to the brain triggers a series of electrical bursts, leading to tunnel visions and bright lights. Some researchers believe NDEs could be dream-like experiences that occur as the brain tries to restart itself, similar to what happens during REM sleep. Another theory suggests that the brain's temporal lobe, which controls memory and perception, might generate out-of-body sensations and life reviews when it's under trauma. But here's the problem. None of these theories explain everything. For example, chemical or oxygen deprivation might explain visions and euphoria. But why are the experiences so structured and meaningful? Why do so many people, from so many different backgrounds, report similar sequences and symbols? And even more puzzling, how do some people gain information they shouldn't have had access to, like describing medical equipment, conversations, or procedures that happened while they were unconscious? These questions remain stubbornly unanswered. Then, of course, there are more metaphysical explanations. Some believe that NDs point to consciousness existing separately from the body, that mind and brain are not the same thing. This would suggest that life, or at least consciousness, could somehow survive physical death. It's a possibility that science, rooted in materialism, struggles to accept, but cannot completely rule out. For now, there is no scientific consensus. Near-death experiences remain perched on the edge of two worlds, one foot in neuroscience, the other in mystery. In the end, near-death experiences remind us that despite all our advances, despite all our machines, all our studies, all our scans, the frontier of death remains largely unexplored. And maybe that's the point. Maybe some mysteries aren't meant to be solved, at least, not yet. Because if NDs teach us anything, it's this. The journey at the edge of life is far more mysterious and far more profound than we ever imagined. The mysterious universality of pi. Why this irrational number baffles science. It's just 3 digits, 3.14. But behind those numbers lies one of the deepest mysteries in all of mathematics and science. We're talking about pi, the seemingly simple ratio of a circle's circumference to its diameter. Yet for centuries, pi has been whispering secrets from the edge of infinity. And to this day, no one truly understands why it shows up everywhere. Let's start with what we know. Pi, usually written as the Greek letter pi, is a mathematical constant. Take any perfect circle. Measure the distance around it, the circumference. Then measure straight across through its center, the diameter. Now divide those two numbers. Circumference divide diameter. You get 3.1415926535, and so on, forever. That's right, pi is irrational. which means it never ends and never repeats. We've calculated pi to trillions of digits, and it still hasn't settled into a pattern. So far, so good, right? Just another weird math thing? Well, not quite. Here's where it gets weird. Pi doesn't just show up in circles. It appears in equations that have nothing to do with geometry. It pops up in quantum mechanics, in probability, in electromagnetism, even in the formula for calculating the structure of DNA. It shows up when you calculate the Gaussian integral, an equation that has absolutely no circles in it. And get this, pi is in Einstein's field equations of general relativity, in Heisenberg's uncertainty principle, and in the equations used to describe the structure of black holes. In short, pi is everywhere, not just in math, but in nature and reality itself. This universality of pi is what baffles scientists and mathematicians alike. Why would a number that originally described circles show up in equations about time, space, and the behavior of particles at the quantum level? Why is this one number embedded so deeply into the fabric of our universe? Nobody knows. Some theories suggest that pi is a kind of mathematical fingerprint of our universe, that its recurrence in physics and nature isn't a coincidence, but a clue. A clue that reality itself might be rooted in mathematics. Others argue it's just a consequence of how we define our measurement systems, that any universe with similar geometry would have similar constants. But even that doesn't explain why pi appears in areas with no geometry at all. It's like pi is a universal language, speaking across space, energy, and matter. And then there's the digital mystery. Because pi is irrational, its decimal expansion goes on forever. But despite all our calculations, we've never found a repeating pattern. There's no cycle, no loop, just infinite chaos that somehow still describes order. Mathematicians believe pi may be normal, a number where every digit from 0 to 9 appears equally often, with perfect statistical randomness. But here's the thing. No one has ever proven that pi is normal. That means that the digits of pi might look random, but could contain hidden patterns that we haven't discovered yet. What if those patterns hold keys to something deeper, something about the nature of reality itself? So, where does that leave us? Pi is a number that should just belong to circles, but instead, it haunts black holes, quantum particles, and the structure of the universe. We don't know why it's everywhere. We don't know if its digits hide secrets we haven't unlocked. And we certainly don't know why reality bends itself around this irrational constant. All we know is this: pi isn't just a number, it might be a cosmic code. And for now, it remains one of the greatest unsolved mysteries in both math and science. The Antikythera mechanism, the 2,000-year-old computer that shouldn't exist. It was the year 1901. Divers exploring a Roman era shipwreck off the coast of Antikythera, a tiny Greek island, were expecting treasures. Maybe some amphorae, maybe some statues. What they didn't expect was to find a machine, a device so complex, so intricate, that it would baffle scientists for more than a century. This is the story of the Antikythera mechanism, a 2,000-year-old artifact that has been called the world's first computer and one of the most mysterious technological relics ever discovered. Let's break it down. At first glance, It looked like nothing more than a lump of corroded bronze. But as experts cleaned and analyzed the fragments, they realized they were staring at an ancient analog device filled with gears, over 30 bronze gears, each with teeth cut with precision almost impossible for its time. The mechanism is believed to have been built sometime between 150 and 100 BCE. And that's what makes it so unbelievable. Because back then, humanity wasn't supposed to have this kind of technology. So, what did it do? The Antikythera mechanism wasn't decorative. It wasn't a clock. It was a scientific instrument, an ancient astronomical calculator. It could predict the positions of the sun, the moon, and possibly the five known planets decades into the future. It also tracked the phases of the moon, eclipses, and even the timing of the ancient Olympic Games. It used differential gearing, something modern engineers didn't invent until the 16th century. This was millennia ahead of its time. And this is where the mystery deepens. How did ancient Greek craftsmen, working with primitive tools, no microscopes, no lathes, create a mechanism of such astonishing precision? Some of the gear teeth are barely a millimeter wide. The mechanism features a system of epicyclic gears, previously thought to be invented over 1,000 years later. Historians once assumed that ancient cultures lacked this kind of engineering sophistication. The Antikythera mechanism has blown that assumption out of the water. Even today, we haven't fully cracked its code. CT scans and 3D modeling have revealed inscriptions, hidden instructions etched in Greek that help explain what some of the dials were for. But huge chunks of the mechanism are missing. We only have about a third of the original device. The rest, lost to time or still on the seabed. We don't even know who built it. Some believe it was designed by Hipparchus, the father of trigonometry. Others think it was inspired by the work of Archimedes. But no text from the era describes such a machine. No other artifact like it has ever been found. And that's what makes it so strange. The Antikythera mechanism isn't just an outlier. It's an orphan of history, a glimpse into a level of ancient technological sophistication that seems to vanish immediately after it appears. Why haven't we found more like it? Did ancient civilizations have more advanced tech than we realize? Or was this simply a one-off masterpiece, the product of a singular genius whose work was lost in time? And if that's the case, what else might have been invented and forgotten? In the end, the Antikythera mechanism stands as a humbling reminder. There are gaps in our understanding of history, moments where the timeline doesn't quite add up, artifacts that whisper, there's more to the past than we think. So when we talk about unsolved scientific mysteries, this one deserves a top spot. Because the Antikythera mechanism isn't just a machine. It's a message from the ancient world, one we're still trying to decode. Phantom limb pain, the pain that shouldn't exist. Imagine losing an arm or a leg, an incredibly traumatic event. But now imagine this: weeks, months, or even years after the amputation. You still feel it. You feel the hand that's no longer there. The fingers itch. The arm aches. The foot burns. You try to scratch it, but there's nothing there to scratch. Welcome to the bizarre and haunting world of phantom limb pain, a phenomenon where amputees feel vivid sensations, including intense pain, in limbs that have been surgically removed. It's one of medicine's strangest, most frustrating puzzles. And here's the kicker, it's incredibly common. Up to 80% of amputees report phantom sensations. Many feel pain, not mild discomfort, searing, stabbing, burning pain, in a part of the body that doesn't even exist anymore. So, how is this possible? First, let's separate two related phenomena. There's phantom limb sensation, which is the feeling that the limb is still there. This can be neutral or even comforting. Then there's phantom limb pain, which is often distressing, disabling, and persistent. Now you might think this would be simple to explain. Maybe it's just psychological, right? Wrong. Modern brain scans show that phantom limb pain is very real. The brain lights up in response to it. In fact, some areas of the brain seem to behave as though the missing limb is still part of the body. This brings us to one leading theory, the neuromatrix theory. Your brain holds a mental map of your body called the body schema. When a limb is removed, that map doesn't get erased. The brain still expects signals from the missing body part. And when it doesn't receive those signals, it starts misfiring. That's when pain arises, generated not in the missing limb, but in the brain itself. So why can't we just rewire the brain or update the body map? That's the million-dollar question. Some treatments try. One of the most famous is the mirror box therapy developed by neuroscientist V.S. Ramachandran. It's deceptively simple. The patient places their intact limb in one side of a box with a mirror in the middle, creating the illusion that the missing limb has returned. Then, by moving the real limb, the brain sees the reflection and gets tricked into thinking the phantom limb is moving too. And amazingly, sometimes this works. The pain goes away, but not always. Some patients get no relief. Others get worse. The results are unpredictable. Other treatments like medications, nerve stimulation, and even virtual reality have been tested. Still, there is no universal cure. Another mystery is why the pain varies so wildly between individuals. Some people develop phantom pain immediately. Others, not for years. Some feel it constantly. Others feel it only in bursts. And strangely, even people born without limbs sometimes report phantom sensations. Wait, what? Yes, people who never had an arm or leg can still feel pain in a limb they never possessed. This suggests that the brain comes pre-programmed with a body map, even if the body doesn't match it. Let that sink in. So what does all this tell us? Phantom limb pain reveals something profound. Pain isn't just physical. It's neurological. It's psychological. It's deeply tied to identity and perception. We still don't fully understand how pain works in the brain, why some neural circuits refuse to shut off, why the brain keeps clinging to a body part that's long gone. In the end, phantom limb pain is a paradox, the pain of absence, a real sensation generated from something that no longer exists. And until we understand the full complexity of the brain's mapping, memory, and sensory systems, this ghostly pain will continue to haunt patients and baffle science. The mind-bending precision of the pyramids of Giza. Imagine trying to build something so massive, so precise, that thousands of years later, modern engineers are still scratching their heads in disbelief. Welcome to the Great Pyramids of Giza. These ancient monuments, built over 4,500 years ago, aren't just architectural wonders, they're astronomical enigmas. Because the Great Pyramid of Khufu, the largest of the three, is aligned to true north with a precision of less than 0.05 degrees. Let me say that again. Less than 3 arc minutes off perfect alignment. That's more accurate than most modern buildings, built by hand, with stone tools, in the Bronze Age. So, how on earth did ancient Egyptians do it? Let's break down the mystery. The Great Pyramid's four sides are almost perfectly aligned to the cardinal directions: north, south, east, and west. Not magnetic north, true north, the rotational axis of the Earth. No compasses existed then. No satellite GPS. No laser levels. Just copper chisels, wooden sleds, and, apparently, an astonishing understanding of the cosmos. But it gets even weirder. All three pyramids at Giza aren't just aligned individually. As a group, they're arranged in a pattern that closely mirrors the three stars of Orion's belt, an idea popularized in the 1990s as the Orion correlation theory. And while that theory is still debated, no one argues this. The placement, orientation, and design of these pyramids involve a level of precision we can't fully explain. So, what are the possible explanations? One theory is that the Egyptians used the stars themselves to align the structures. Specifically, some researchers believe they could have tracked the movement of circumpolar stars, which rotate around the North Star. Another theory suggests they observed the sun's shadow using a vertical stick called a gnomon and tracked its shortest shadow at noon over the year to determine true north. Sounds simple? Not really. That method is susceptible to atmospheric distortion, seasonal changes, and human error. To consistently achieve such small margins of error across millions of limestone blocks, some weighing over 80 tons, seems almost impossible. And here's another kicker. Even modern attempts to replicate this alignment using ancient tools have failed to reach the same level of accuracy. So, what does this tell us? Either the ancient Egyptians had techniques we've forgotten, or their knowledge of astronomy and surveying was far more advanced than we've ever given them credit for. And the questions don't stop at alignment. How did they transport and place these massive stones so precisely? How did they maintain straight lines and consistent angles over such enormous distances? And why were they so obsessed with perfect orientation to the Earth and sky? Some fringe theories have suggested alien intervention or lost civilizations, but mainstream science hasn't needed to go that far yet. Still, no one has provided a definitive answer. So here's where we stand. The pyramids of Giza were not just tombs. They were mathematical, astronomical, and architectural statements. They embody a level of intentionality and skill that baffles modern experts. And the truth is, we still don't know how they did it. It's one of those historical anomalies that forces us to pause and ask, what else have we underestimated about ancient civilizations? Because the pyramids aren't just standing stones. They're a message, etched in limestone, aligned with the stars, and echoing through the ages. Why is gravity so freaking weak? All right, let's talk about gravity. You know, the force that keeps your feet on the ground, the planets in orbit, and your coffee cup from floating away. It feels strong, right? But here's the kicker. Scientifically speaking, gravity is ridiculously, laughably weak. Let's compare. Take a paperclip. Now use a small magnet to lift it off the table. That tiny magnet just overpowered the gravitational pull of the entire planet Earth. That's not just weird, it's a cosmic insult to gravity. And physicists have been trying to figure out why gravity is so weak compared to the other fundamental forces of nature. And they still don't have a solid answer. So, what do we mean by weak? There are four fundamental forces in the universe. The strong nuclear force binds protons and neutrons together. The electromagnetic force controls electricity, magnetism, light. The weak nuclear force responsible for radioactive decay. And then there's gravity pulling things together. Now here's where it gets weird. The strong nuclear force is about minus 0 cube times stronger than gravity. Yes, that's a 1 with 38 zeros behind it. That's like comparing an ant to the entire mass of the Earth. So, what gives? Why is gravity, this seemingly all-important force, so absurdly feeble? Physicists have come up with a few ideas. One of the most compelling is called the hierarchy problem. It asks, why is gravity so much weaker than the other forces? Is there a deeper reason? Or is it just a weird coincidence? Some theories suggest that gravity might not be weak at all. We just experience a watered-down version of it. Enter extra dimensions. No, not science fiction, real physics. In string theory and other advanced models, our universe may have more than the three spatial dimensions we experience. Gravity, according to these theories, might actually be spreading out into these hidden dimensions, like water leaking from a hose. That would make gravity seem weak in our 3D world. But in the full dimensional space, it could be just as strong as the other forces. Cool theory, right? But here's the problem. So far, there's zero experimental evidence for extra dimensions. No one's found them. No one's proved them. And that brings us back to square one. Another idea. Maybe gravity isn't a real force at all. Some physicists have proposed that it could be an emergent property, something that arises from the collective behavior of quantum particles and spacetime itself. Imagine gravity as the shadow of something deeper we haven't discovered yet. A side effect, not a fundamental force. But again, fascinating idea. No concrete proof. So where are we now? We've measured gravity. We've modeled it. We've even sent satellites into space to study its effects on distant objects. And yet, we still don't know why it's so incredibly weak. It's the most familiar force in your life, yet it's also one of the most mysterious. Until we figure it out, we're left with an annoying paradox. Gravity runs the cosmos, sculpts galaxies, and holds our universe together. But a refrigerator magnet can beat it in a one-on-one fight. So next time you drop your phone and curse gravity, remember, it may be the most confusing force in physics. It's holding your world together, but it's barely hanging on. And that, folks, is one of science's biggest unanswered questions. Tardigrades, nature's ultimate survivors that defy science. Imagine a creature so tough that it can survive the freezing vacuum of space, the crushing pressure of the deep ocean, and temperatures hotter than boiling water. Sounds like science fiction, right? Well, meet the tardigrade, also known as the water bear. These tiny, eight-legged microanimals are some of the most indestructible creatures on Earth. And here's the kicker. Science still doesn't fully understand how they pull it off. Tardigrades are microscopic, less than a millimeter long. You could fit dozens of them on the head of a pin. But despite their size, they're absolute tanks when it comes to survival. Over the years, experiments have shown that tardigrades can survive temperatures as low as minus 272 degrees Celsius, almost absolute zero, and as high as 150 degrees Celsius, way beyond boiling. Intense radiation that would kill humans many times over. Crushing pressures greater than those found in the deepest parts of the ocean. Complete dehydration for decades. Yes, decades, only to come back to life with a little water. And even the vacuum and radiation of outer space. When humans sent tardigrades on a space mission in 2007, they endured the trip, came back, and kept on living. No other complex organism has shown such resilience. So, what's their secret? Scientists know part of the answer. Tardigrades have a special survival trick called cryptobiosis. When conditions get harsh, they curl up into a tiny ball called a ton, drastically slowing down their metabolism to almost zero. In this ton state, they can survive extreme environments for years, maybe even centuries. It's like pressing a biological pause button. Their bodies produce unique sugar molecules, like trehalose, that help protect their cells from damage. They also make special proteins, like DSUP, short for damage suppressor, which literally shield their DNA from radiation and oxidative damage. These mechanisms are amazing. But here's the weird part. Even with all these discoveries, science still doesn't fully understand how tardigrades survive such extreme extremes. For one, the ton state is incredibly complex. Scientists are still trying to figure out how tardigrades prevent their cells from crystallizing when they lose almost all their water. In most organisms, dehydration shreds cell membranes and proteins beyond repair. But tardigrades somehow preserve their entire biological structure. Also, not all tardigrades survive the same way. Different species seem to use slightly different strategies, suggesting multiple, overlapping methods of survival that we still haven't fully decoded. And while we know about a few key proteins and sugars, how all these systems interact at the molecular and genetic level remains a mystery. How does their DNA repair itself after heavy radiation damage? How do their proteins avoid denaturing in extreme heat? How exactly do they manage near total metabolic shutdown without fatal damage? We're still piecing it together. The mystery of tardigrades matters for more than just curiosity. If we can crack their secrets, it could lead to breakthroughs like better ways to preserve food and medicine, new methods for protecting astronauts from space radiation, potential techniques for organ preservation, extending the time donated organs can survive before transplantation, clues for human survival in extreme environments, even on other planets. In a very real way, tardigrades could hold the key to pushing the boundaries of human exploration and medicine. At the end of the day, tardigrades show us that nature's toolkit is far bigger and stranger than we ever imagined. They're a living reminder that some of Earth's greatest mysteries come in the tiniest, toughest packages. And despite all our technology, all our scientific knowledge, the humble water bear continues to baffle us, surviving where nothing else can, thriving in places we can barely comprehend. The double slit experiment, the experiment that broke reality. Let me tell you about the most famous science experiment that has absolutely no business making sense. It's called the double slit experiment, and it straight up broke reality. At first glance, it sounds simple. Take a wall, cut two vertical slits in it. Now fire some tiny particles, like electrons or photons, through those slits. Behind the slits, put a screen to see where they land. No big deal, right? But then, everything goes off the rails. Let's start with expectations. If you fire little particles, like tiny bullets, through the two slits, you'd expect to see two bands on the screen where the particles hit. Just like throwing baseballs through two windows, two spots, right? And that's exactly what happens if you observe which slit each particle goes through. But here's where the weirdness begins. If you don't observe the slits, if you just let the particles fly without checking, they start to behave like waves, not particles. Suddenly, you don't get two bands on the screen. You get an interference pattern, like ripples in water overlapping. The particles act like they went through both slits at the same time, interfered with themselves, and only then decided where to land. How? Nobody knows. So naturally, scientists got curious. They said, let's sneak a peek and see which slit each particle goes through. Yes, what happens? The moment you observe which slit they use, boom, the interference pattern disappears. The particles go back to acting like regular little bullets again. It's like the particle knows it's being watched, and it changes its behavior based on that. What the hell? This isn't just weird, it's quantum weird. And it's not some fringe experiment. It's been replicated hundreds of times with electrons, protons, atoms, even large molecules. Every time, it reinforces the same unsettling message. Observation changes reality. That's not a metaphor. In the quantum world, measuring something actually affects how it behaves. This leads us to the giant elephant in the room. What does it mean to observe something? Do we need a human observer? Or is a machine enough? What counts as a measurement? Where exactly does the collapse from wave to particle happen? Nobody knows. Physicists have argued about this for nearly a century. There are theories. Some say particles exist in a cloud of probabilities until measured. Others propose the many worlds interpretation, that each possibility happens in a different universe. Some think consciousness itself might play a role, but so far, no one has cracked it. The double slit experiment is like reality's glitch in the matrix. It says, you thought the world was made of solid objects moving around in space and time? Think again. It shows us that at the most fundamental level, the universe doesn't behave in ways we can intuitively understand. Particles act like waves until we look. Then they suddenly act like particles again. And it's not just philosophical. This is the foundation of quantum mechanics, which powers your phone, GPS, computers, and more. Yet, we still don't fully understand what's going on beneath the hood. So next time someone tells you that science has everything figured out, tell them about the experiment where reality changed because someone watched. Tell them about the double slit experiment and how it shattered our ideas of certainty, objectivity, and what it means to know anything at all. Because the more we learn about the quantum world, the less sense it seems to make. Why we sleep, a mystery sense still can't crack. Let's get one thing straight. We spend about a third of our lives asleep. That's around 25 years of your life, unconscious, drooling into a pillow, doing absolutely nothing. Or so it seems. You'd think that by now, with all our scientific knowledge, we'd have a clear, definitive answer to the question, why do we sleep? And yet, we don't. That's right. Despite decades of research, the real reason why we need sleep remains one of the biggest unsolved mysteries in all of science. Let's start with the basics. We know what happens if we don't sleep. We get cranky. We lose focus. Memory fails. The immune system weakens. And eventually, we die. Yes, you can literally die from sleep deprivation. So clearly, sleep is essential. But why? That's the million-dollar question. For a long time, scientists assumed sleep was just the body's way of resting to conserve energy. But that doesn't really make sense. See, from an evolutionary standpoint, sleep is kind of stupid. You're unconscious for hours, unaware of predators, unable to eat, reproduce, or protect yourself. If evolution is about survival, how did sleep survive evolution? There must be something so important about sleep that it outweighs all those risks. So, what could that be? Well, researchers have come up with a bunch of theories. One popular idea is memory consolidation. During sleep, especially during REM, rapid eye movement sleep, your brain replays experiences and files them away, like saving files to a hard drive. Makes sense, right? But here's the catch. We can still form memories without sleep. And while sleep helps, it's not essential for memory in all creatures. So that can't be the whole answer. Another theory is that sleep is for brain maintenance, a kind of night shift cleaning crew. In 2013, scientists discovered something called the glymphatic system, a kind of drainage system in the brain that clears out toxic waste during sleep, including proteins linked to Alzheimer's. It's like your brain takes out the trash, but only while you're unconscious. Again, fascinating. But is that why we evolved to sleep? Or just a benefit of sleeping? We still don't know. There's also the idea that sleep is crucial for emotional regulation, immune health, cell repair, hormone balancing, and more. And here's the kicker. Every animal species sleeps in some form. From humans to cats to birds to jellyfish. Yes, jellyfish. All living things seem to shut down, at least partially, on a regular basis. Even fruit flies show signs of sleep-like behavior, which means sleep is not some quirky human habit. It's a universal biological necessity. But why? Here's where the mystery deepens. Sleep is so essential, yet we don't fully understand what flips the switch that tells us it's time to sleep. We know about melatonin, circadian rhythms, sleep cycles, but the core reason your brain and body say, okay, lights out now, is still not fully understood. It's like the more we study sleep, the more complex and weird it becomes. And here's a real kicker. Some people don't need sleep. A rare genetic mutation found in a few families allows them to function perfectly on just 4 hours a night. How does that work? What does that say about the rest of us? We don't know. So, where does that leave us? We know that sleep is critical for survival, that it's deeply tied to our health, memory, and sanity. But we still don't have a complete answer to the question, why do we sleep at all? It's like nature's most ancient mystery, hiding in plain sight every single night. So tonight, when you lie down, close your eyes and drift off, just remember, you're doing something science still can't fully explain. The Montauk Monster, what the hell was that thing? In July of 2008, something bizarre washed up on the shores of Montauk, Long Island, and it looked like it had crawled straight out of a nightmare. A bloated, hairless body, grayish pink skin, sharp teeth, clawed limbs, and a beak like snout. Locals didn't know what to make of it. Was it a mutant? A genetic experiment? An alien? They just called it the Montauk Monster. And more than 15 years later, we still don't know exactly what it was. It all began when a group of friends stumbled across a decaying creature on Ditch Plains Beach, near the tip of Long Island. Shocked by the thing's appearance, they snapped a photo, and that photo exploded across the internet. It hit blogs, newspapers, and eventually made its way to major news networks. Theories flew in from every corner of the web. Some claimed it was a raccoon, others said a dog, a sea turtle without its shell, or even a pig. But here's the twist, none of the explanations quite matched the photo. The creature had features that didn't line up with any known animal. Let's break it down. It had 5 fingers on each front limb, like a raccoon or primate. It had a beak-like mouth, which no raccoon or dog has. Its back legs were shaped oddly, with a stance and length unusual for known mammals. Its skin was almost completely hairless, leathery, and discolored, possibly from decay, but still bizarre looking. And then there's the tail, or lack of one, which threw even more confusion into the mix. So, what was this thing? A raccoon? A mutated sea creature? Some Frankenstein animal? Or something even stranger? One of the most popular theories was that the creature was an escaped experiment from the nearby Plum Island Animal Disease Center, a government facility just a few miles away, known for researching contagious livestock diseases. Plum Island has long been the center of conspiracy theories, with whispers of secret genetic testing and biological weapons development. So when a grotesque creature washed ashore nearby, people naturally started to connect the dots. Was this a failed genetic hybrid? A bio-experiment that went wrong? No one from Plum Island confirmed or denied anything. And with no official investigation launched, the rumors kept growing. Eventually, some scientists chimed in. They claimed the Montauk Monster was most likely a raccoon, and that the strange appearance could be explained by decomposition, which can distort an animal's features, cause fur loss, and expose bone. The beak-like snout? Maybe just exposed jawbone. The odd posture? The result of bloating and decay. But here's the thing, no autopsy was ever performed. The body reportedly disappeared. Some say it was taken away by officials. Others say a local buried it. Some claim the original group took it and never revealed where it went. So all we're left with, is that single photo. And that's what makes the Montauk monster so baffling. In an age where everything can be traced, tested, and documented, this creature washed up out of nowhere, shocked the public, vanished without a trace, and was never conclusively identified. No DNA tests, no second look, no closure, just a viral image and a trail of questions. So, what was the Montauk monster? A raccoon distorted by nature? A government experiment gone wrong? Or something else entirely? Until we get more evidence, if we ever do, it remains one of the most unsettling, unexplained creature sightings of the 21st century. Sometimes, the strangest mysteries don't come from deep space. They just wash up on the beach. Havana Syndrome, the invisible threat no one can explain. In late 2016, U.S. and Canadian diplomats stationed in Havana, Cuba, began reporting strange and terrifying symptoms. They heard high-pitched, piercing noises, felt pressure in their heads, experienced nausea, vertigo, headaches, memory loss, even brain injuries. But there was no visible attacker, no gas, no virus, no proof of physical harm, only confusion, fear, and pain. This was the beginning of what would come to be known as Havana Syndrome, a bizarre and still unexplained health phenomenon that has spread across continents and baffled some of the brightest minds in science and national security. Let's break down what happened. The first reported cases came from American diplomats in Havana. They described sudden sensations of sound, buzzing, grinding, or humming that seemed to follow them even when they moved. Some reported being physically knocked off balance. Others said the sensations stopped the moment they left the room. And afterward, many were diagnosed with traumatic brain injuries, with no sign of blunt force trauma. Naturally, the CIA and U.S. State Department were alarmed. Was this an attack? A new kind of weapon? Mass hysteria? But things only got stranger. Soon, reports began coming in from around the globe. China, Uzbekistan, Russia, Colombia, even Washington, D.C. U.S. intelligence officers, diplomats, and military personnel were experiencing the same symptoms: sudden dizziness, confusion, nausea, tinnitus, and brain fog. Some incidents occurred inside hotel rooms, others outside embassies. Some were so severe that people had to retire from duty entirely. And in almost every case, there was no sign of an environmental cause, no toxic exposure, no virus, no bacteria, just symptoms and silence. So, what are the theories? One of the leading ideas is that Havana Syndrome is the result of a directed energy weapon, possibly using microwaves or ultrasonic frequencies to disrupt brain function without leaving a trace. In fact, a 2020 report by the National Academies of Sciences concluded that directed, pulsed radio frequency energy was a plausible explanation for many of the cases. But if that's true, who has this technology? And why would they target diplomats, often in secure buildings, across multiple countries? Was it Russia? China? A rogue actor? Or is the tech more common than we think? There are no answers. No country has admitted involvement. No device has ever been recovered. And no hard evidence has surfaced to confirm it's a weapon at all. Another theory is mass psychogenic illness, or mass hysteria. This is when a group of people, often under stress, begin to exhibit similar symptoms without any physical cause. It's happened before in history, usually in tight knit, high pressure groups. But here's the problem: Havana syndrome isn't just headaches and nausea. Many victims showed measurable signs of brain injury, including changes in white matter and vestibular damage, the kind of thing you don't just imagine into existence. So, what gives? How do you reconcile objective neurological trauma with invisible causes? Science doesn't have a satisfying answer. Not yet. And this is why Havana syndrome baffles experts to this day. It straddles the line between medicine, national security, and psychology. It affects real people in real ways, but without the kind of evidence that science usually demands. It's part mystery illness, part spy thriller, part science fiction. And worst of all, if it is an energy weapon, then it means there's a technology out there that can harm you without ever touching you. That's a terrifying possibility. So, where do we stand today? Investigations are still ongoing. The US government has spent millions looking into it. New cases continue to surface. Victims continue to suffer. And science continues to scratch its head. Whether it's a foreign weapon, a new kind of illness, or something else entirely, Havana syndrome remains one of the most chilling unexplained phenomena of our time. Because sometimes the most dangerous threats are the ones you can't see. Why we laugh, the weird mystery science still can't fully explain. Laughter. It's something we all do. We chuckle, we giggle, we howl, we snort, often without even thinking about it. But here's the weird thing: we don't actually know why. Seriously, laughter is one of the most common human behaviors, yet it remains one of the least understood. It's not just a response to jokes. Babies do it before they can speak. We laugh when we're nervous, when we're tickled, even when nothing funny is happening. So, what is laughter? A social signal? A brain glitch? An evolutionary tool? Well, that's where things get murky. Let's break it down. First off, what actually happens when you laugh? Laughter is a complex process involving multiple regions of the brain: the prefrontal cortex, where we process social context, the amygdala linked to emotions, and even the motor cortex, which controls the physical act of laughing. It also engages your respiratory system, facial muscles, and even your heart. One hearty laugh can trigger the same physiological response as light exercise. But that still doesn't tell us why we laugh. Historically, some scientists have argued that laughter is an evolutionary relic, a way for early humans to signal that everything was safe. Say you're out in the jungle, and someone hears a rustle in the bushes. Tension spikes. Maybe it's a predator. But then someone realizes it's just a bird and starts laughing. That laughter becomes a nonverbal way to tell the group, false alarm, everyone relax. According to this theory, laughter is basically a social release valve. It diffuses tension, signals safety, and helps bond groups together. But while this explains some types of laughter, it doesn't explain why we laugh at jokes, sarcasm, or absurdity, things that involve layers of meaning and intellect. In fact, we're the only species that laughs at language-based humor. That leads us to the incongruity theory, one of the oldest ideas in philosophy. It says we laugh when something unexpected happens, but not in a threatening way. For example, if someone slips on a banana peel but gets up unharmed, that surprise, mixed with relief, triggers laughter. But here's the problem: not everyone laughs at the same things. Humor is wildly subjective. What one culture finds hilarious, another finds offensive. What makes one person belly laugh leaves another stone faced. If laughter were just a response to surprise or absurdity, why is it so inconsistent? Then there's the social side of things. Studies show we're 30 times more likely to laugh in a group than when we're alone, even if we're hearing the exact same joke. Laughter seems to be contagious, and socially contagious at that. In fact, most of the time when people laugh, it's not in response to something funny, it's in response to other people. A way of saying, I get you, or I belong. So is laughter really about comedy, or is it about connection? And here's where science hits a wall. Because laughter doesn't fit neatly into any one category. It's emotional, it's cognitive, it's physical, it's social. It spans psychology, neuroscience, anthropology, and even linguistics. There is no single laughter center in the brain. No one size fits all trigger. No definitive explanation for why we evolved to laugh at all. Yes, there are theories, plenty of them, but no consensus. And that's why laughter baffles science. It's universal, but inconsistent. It's involuntary, but also manipulable. It's joyful, but sometimes happens during grief or fear. It's one of the most human things we do, and yet, after centuries of inquiry, we still can't say for certain why it exists. Maybe laughter, like consciousness or love, is just one of those things science can describe, but never fully explain. And maybe that's okay, because as long as we keep laughing, the mystery lives on. The origin of language, science's biggest communication breakdown. Let's start with a simple question. Where did language come from? Not the English language, or Spanish, or Chinese, but language itself. The human ability to take thoughts, feelings, and abstract ideas, and convert them into sound, gesture, or symbols that others can understand. It's the superpower that sets us apart from every other species on Earth. But here's the wild part. Science still has no idea how it started. Despite decades of research across linguistics, anthropology, neuroscience, and evolutionary biology, the origin of language remains one of the great unsolved mysteries of the human story. Let's take a step back. Every human culture, no matter how isolated, has developed some form of language. This suggests that the ability to communicate through structured speech is wired into our biology. But when did that wiring happen? Was it 50,000 years ago? 100,000? Longer? We don't know. And here's the first big problem. Language doesn't fossilize. You can dig up bones. You can study tools. But you can't unearth a conversation. The earliest physical clues we have, like symbolic art or changes in the shape of the skull, only suggest possibilities, not proof. So, what about studying modern day hunter gatherer tribes or isolated populations? Well, that gives us insights into how language works, but not how it started. Which brings us to Theory 1, the divine gift theory. This was the ancient belief, held by philosophers like Socrates and early theologians, that language was given to humans by a god or higher power. It's less science, more spiritual explanation. That was eventually replaced by theory issue, the imitation hypothesis, the idea that humans developed language by mimicking natural sounds. Birds chirping, wolves howling, rivers flowing. But there's a problem with that. Animal sounds aren't language. They're signals, yes, but they're not complex, layered systems with grammar and syntax, which leads to the gesture first theory. Some scientists believe language may have started as sign language, hand movements, and facial expressions used by early humans before the vocal cords caught up. This makes sense, considering primates use gestures to communicate even today. But it doesn't explain how we made the massive leap from pointing and grunting to Shakespeare, or memes, or podcasts. Then there's the tool making hypothesis, the idea that the brain areas responsible for fine motor skills in tool use may have overlapped with those that developed into language centers. Basically, the smarter we got with our hands, the better we got at talking. And yet, tool use has been observed in chimpanzees, crows, even sea otters, none of whom developed a language system anywhere near ours. So, what gives? Why us? And why then? Modern linguists have identified some key traits that make human language unique. It's compositional. We build infinite meanings from finite parts. It's symbolic. Words represent abstract things. It's recursive. We can embed ideas within ideas. And it's social. Language shapes how we think and connect. Yet, no current theory can explain how all of these features came together in one species. Even the timeline is fuzzy. Did it emerge gradually over hundreds of thousands of years? Or did it explode suddenly, like a cognitive Big Bang? Evolutionary science is great at explaining why traits are useful, but not always how they appeared in the first place. And the deeper we dig, the more complicated it gets. So, why does the origin of language baffle science? Because it sits at the intersection of biology, cognition, culture, and history. And we lack the physical evidence, the testable theories, and the time machine to ever be certain. But maybe that's what makes it beautiful. Because every time we speak, listen, read, or laugh, we're participating in one of evolution's greatest unsolved riddles. And that's a mystery worth talking about.